So to continue with our study of polynomial functions, section 3.4 is the zeros of polynomial functions. We've already done some of this, the homework problems that we were just doing from review, we were finding the zeros, but we're going to get a bit more information here in section 3.4. In particular, we're going to learn about the rational zero theorem, and that's going to help us to find the possible rational zeros. And then from there, we'll use that to find the zeros and to solve polynomial equations, and to think about the linear factorization theorem and then Descartes' rule of signs. Okay, so the rational zero theorem, this is our big theorem for section 3.4. It says if you're given a polynomial function and it has integer coefficients, and so it must have integer coefficients in order for the rational zero theorem to work. And P over Q, where P over Q is reduced to lowest terms, is a rational zero of f, then P is a factor of the constant term. So what I want you to make a note of is that whatever the constant is, the one that doesn't have any x's in it, the factors of this give you what we're going to call our P's. And Q is a factor of the leading coefficient, A sub n. And so over here, A sub n is the coefficient in front of the highest power on x, and its factors give us our Q's. Okay, so our P's are going to come from, if you have your polynomial written in descending powers on x, your P's will come from the factors of the last term, and your Q's will come from the coefficients on the first term. What this says is if you have a rational zero, the rational zero will come from numbers that are P's over Q's. So let's see what this looks like. List all possible rational zeros of f of x. Our P's will come from the -3, and our Q's will come from 4. So I'm going to list out what my possible P's are. P's are going to be numbers that multiply to give us a -3. +1 with a -3, and -1 with a +3. Okay. Oftentimes we're going to write this just a more simplified way, plus or minus 1, plus or minus 3. Okay. Those are our possible P's. Now our Q's are numbers that multiply to give us 4. So 1 times 4, or -1 times -4, right? So plus or minus 1 with plus or minus 4. But also 2 times 2 and -2 times -2. So plus or minus 2 goes in there as well. Okay, so those are our Q's. List all possible rational zeros. So now all we do is take every P and put it over every Q. So possible rational zeros say to take every P and put it over every Q. So let's start with plus or minus 1, and it can go over plus or minus 1. So I'm sticking with P's plus or minus 1. It can go over plus or minus 2. So 1 over 1, 1 over 2, and then 1 over the 4. Plus or minus 1 over plus or minus 4. That takes care of all the P's of plus and minus 1. Now we go to the next P. Plus or minus 3 is going to go over 1, 2, and 4. Plus or minus 3 over plus or minus 1. Plus or minus 3 over plus or minus 2. Plus or minus 3 over plus or minus 4. That's putting every P over every Q. Okay? Now we just simplify. Plus or minus 1 over plus or minus 1, that's just a plus or minus 1. 1 over 1 is 1 plus or minus. Next one simplifies to plus or minus 1/2. The next one simplifies to plus or minus 1/4, plus or minus 3, plus or minus 3/2, plus or minus 3/4. So, let's think about what this is giving us. Remember how in your homework from section 3.3, they would give you, let's say, a cubic polynomial, and they would tell you what one of the roots was. And then you would be able to find the others. Well, now the rational zero theorem gives us a list of possible roots. So if we're going to have rational zeros of this 5th degree function, those rational zeros must come from this list here. So we're not just having to take random choices for these rational zeros. We have a lot of choices. This does not say that every one of these is a rational zero, but it says that the rational zeros of our 5th degree function will come from these 12 choices. 2, 4, 6, 8, 10, 12. So we have 12 choices. Now, we'll also learn that this 5th degree polynomial can have at most 5 zeros. And so we know all of these 12 won't be zeros, but the rational zeros will come from this list. So it gives us a place to start. Okay? And that's all this one said, was just list the possible rational zeros, not to find the actual zeros. So we're just getting started. This was having us get used to the rational zero theorem. Questions on P's, Q's, and P's over Q's? All right. So now we're going to actually find all the zeros. So we're going to use the rational zero theorem to give us a list of possible zeros, and then we're going to find the actual zeros. So remember your P's, we make sure that our function's in descending powers of x, and it is. We go from cube to square to the 1st degree to the constant. Remember our P's come from the final value, and remember that there is a 1 in front of that x cubed, so our Q's come from the 1. Numbers that multiply to give me -2, well, that's plus or minus 1 times plus or minus 2. And that's it for P's. This one's going to be a little bit simpler. Q, numbers that multiply to give me 1, integer values, well, those are just 1. So I've listed all my P's and all my Q's. Any questions so far? Great. So my possible rational zeros will be plus or minus 1 over plus or minus 1. So remember, we take P's over Q's. Plus or minus 1 over plus or minus 1. And then plus or minus 2 over plus or minus 1. Which simplifies to only plus or minus 1 or plus or minus 2. So right now, there are only 4 possible rational zeros. Any questions on how we got this list? Now, we can use synthetic division to help us figure out which one or ones are the actual zeros, because we want to find the actual zeros. We've listed the possible zeros. Now we want to see which ones actually are zeros. Remember that when you use synthetic division, if you have a 0, you put it in the box, and then if the remainder is 0, that's what the remainder theorem told us. If the remainder after synthetic division is 0, then the number in the box is a 0 of the function. So let's just start with positive 1. If I put 1 in the box, my coefficients are 1, 1, -5, and -2. Where did I get this 1 from? It came from the positive 1 right here. Bring down the 1 and multiply. 1 times 1 is 1. When I add there, I get a 2. 1 times 2 is 2. When I add there, I get a -3. 1 times a -3 is a -3. When I add there, I get a -5. Is 1 a 0 of this function? It's not. This is not, because it's not equal to 0. We need this last number, the remainder, to be 0. So that means that 1 is not a 0 of our function. Let's try -1. So again, taking my same coefficients. So this is trial and error, but the good news is the rational zero theorem gives us our choices, and so we know at least where to start. Bring the 1 down. -1 times 1 is a -1. When I add here, I get 0. -1 times 0 is 0. When I add here, I get -5. -1 times a -5 is a +5. When I add here, I get 3. This is not 0, so -1 is also not a 0 of our function. Moving on in our list, we'll go to the +2. We'll put our 2 in the box. And do it all again. Bring the 1 down. 2 times 1 is 2. When I add here, I get 3. 2 times 3 is 6. When I add here, I get 1. 2 times 1 is 2. When I add, I get 0. Since the remainder is 0, I know that 2 is a 0. Is that okay? All right. Now, at this point, you can either put a -2 in the box and use these reduced coefficients here, or I know that I have a quadratic. And so I can finish solving this because I started off with a cubic polynomial. Since I've found 1 0, that means that what's left here is x squared plus 3x plus 1. Okay? So then using my quadratic formula, so when you have 3 coefficients left, those are your quadratic coefficients. So using my quadratic formula, I'll take -b, which is -3, plus or minus the square root of b squared, 3 times 3, minus 4 times a times c, all over to a. Sorry, y'all. That's -3 plus or minus the square root of 9 minus 4, which is 5, all over 2. And really, that's all you can do with that one. That one doesn't reduce any further. So you have your other 2 zeros here because of the plus and the minus. Okay? So our zeros are 2 and then -3 plus or minus the square root of 5 all over 2. Okay? So had we gone through and put -2 in a box, it wouldn't have given us a 0 either. So it's trial and error until you can reduce your polynomial to a quadratic, and then you can just use the quadratic formula. That's the best way to go. Okay? Questions on this example? It's pretty quiet today. Because it's a rainy Monday morning, or is it because we're confused? Right. Then we'll keep going. Properties of roots of polynomial equations. If a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. And so if you have a polynomial equation, the degree tells you how many roots you can have. Some of them may be repeated, though. So it's not saying unique roots. If a plus bi is a root of a polynomial equation with real coefficients, with b not equal to 0, then the imaginary a minus bi is also a root. We already studied that when we talked about conjugates with imaginaries, but now we're just refreshing ourselves on that. Conjugate zeros will always occur in pairs. If a plus bi is a 0 of a polynomial, then a minus bi is also a 0. All right. We've got 3 examples, just doing the same thing that we have been doing. Remember, our p's will come from the constant, and our q's will come from the leading coefficient. When we think about numbers that multiply to give us a 4, plus or minus 1 and plus or minus 4, and then 2 times 2, so we get plus or minus 2. Whoops. You okay with finding the list of p's? Numbers that multiply to give us negative 4, technically. And then our q's, well, when the leading coefficient is 1, we like it. It makes our list easy. Our q's are just plus or minus 1. So that our possible rational zeros, those are your p's over your q's. If I take plus or minus 1 and put it over plus or minus 1, that's just plus or minus 1. Plus or minus 2 over plus or minus 1, that's plus or minus 2. Plus or minus 4 over plus or minus 1, that's plus or minus 4. We've got 6 options for possible rational zeros. All right, so let's see. Just process of elimination. We'll start with the negative 1. I put negative 1 in the box. My coefficients are 1, negative 2, negative 7, and negative 4. 1, negative 2, negative 7, and negative 4. 1 comes down. I multiply to get a negative 1. Negative 2 plus a negative 1 is a negative 3. Negative 1 times a negative 3 is a positive 3. When I add here, I get a negative 4. Multiplying here gives me a positive 4, and we got lucky on the first try. We found a 0. At this point, I really don't have to try any of the others in the box. Why? Because now I'm left with a quadratic. My quadratic formula is going to tell me the rest of them. Okay. So remember that this is A, this is B, this is C. A negative B plus or minus the square root of B squared minus 4 times A times C, all over 2A. So we get 3 plus or minus the square root of 9 plus 16, all over 2. Nine plus 16 is 25. What's the square root of 25? It's 5. Good. So we get 3 plus or minus 5 all over 2. If I do minus first, 3 minus 5 gives me a negative 2 over 2. So that's a negative 1. 3 plus 5 gives me 8 over 2, and that gives me a 4. So we found them using the quadratic formula. For this one, you could have also found them by continuing on with the options here. So we did find rational zeros that were also in our list. But what does this show you right here? Remember that our first 0 was a negative 1. Let me go back and say one other thing. Remember that you will have n roots or n zeros. N is the degree of the function. Our function was a cubic polynomial. We're going to have 3 zeros here. Some of them can be repeated. Here's 0 number 1 was negative 1, because we found that to be 0. Here's 0 number 2, which is also negative 1, so that was repeated. And then 0 number 3. So those are our 3 zeros. Negative 1 is a 0 of multiplicity 2 because it happened twice. So the actual zeros are -1 and 4. You might just write down that this one is a multiplicity 2, because it happened twice. Questions on this first example? 1 of 3. All right. Same idea, just a different polynomial. What is the degree of this polynomial? It's 3. So our n is 3. We're looking for 3 roots. My p's will come from the 13. And again, we're lucky. This one has, our q's will come from the 1. So my p's are numbers that multiply to give us 13. 13 is a prime number. Just 1 times 13 gives us 13. So we get plus or minus 1 plus or minus 13. The q's are the factors of 1. Well, that's just plus or minus 1. So the possible rational zeros, p's over q's. Plus or minus 1 over plus or minus 1, that's plus or minus 1. Plus or minus 13 over plus or minus 1, then that's just plus or minus 13. Now we go with synthetic division. I'll start with 1 or -1. It doesn't matter which one. Let's go with -1. My coefficients are 1, -5, positive 17, and negative 13. Are there any questions on how or why I'm setting up this synthetic division as I am? We're good? All right. Remember, the 1 comes down, I'll multiply. -1 times positive 1 gives me a -1. When I add there, I get a -6. -1 times -6 is a positive 6. When I add there, I get 23. -1 times 23 is a -23. When you add there, you get a -36. Since that last number, that's our remainder, is not 0, -1 is not a solution to this equation. Let's try the positive 1. I'll bring the 1 down. 1 times 1 is 1. When I add, I'll get a -4. 1 times a -4 is a -4. When I add, I get a positive 13. 1 times 13 is 13. When I add, I've got my 0. So that means that positive 1 is a 0. Since I started with a cubic polynomial, that means this one that's left is quadratic. And so we can use our quadratic formula again with our A, our B, and our C. We'll get -b plus or minus the square root of b squared minus 4 times A times C, all over 2 times A. -b plus or minus the square root of b squared minus 4ac, all over 2a. We get 4 plus or minus the square root of -4 squared is a positive 16, minus 4 times 1 times 13, that's a -52, all over 2. So this gives me 4 plus or minus the square root of a -36. Okay. Notice what's under that square root. It's a negative. That's going to tell you that we have an imaginary solution. So this becomes 4 plus or minus, the square root of 36 is 6. The square root of a negative 1 is I, all over 2. Everything divides by 2 to give me 2 plus or minus 3i. So that gives me my other two solutions. This is where the conjugate pairs comes from. Remember we had a slide a minute ago that said if a plus bi is a root, then a minus bi will also be a root. And it comes from this plus or minus in the quadratic formula. And so the imaginary part is where the plus or minus comes in. And so our list of zeros, we said we'd have 3, and we do. Our zeros come from the positive 1. We get 2 plus 3i and 2 minus 3i. But you can still just write that more simplistically as the plus or minus. Either way would be fine with me. Questions on this second of 3 example? All right, so here's one that's a little bit higher degree polynomial. It'll focus. This one is a degree 4 polynomial. We're looking for 4 roots from this one, okay? So here n equals 4. My p's come from the 4, and my q's come from the 1. Factors of 4, plus or minus 1 with plus or minus 4, plus or minus 2 with itself. The q's are factors of 1. Well, that's just plus or minus 1 again. The possible rational zeros, that's where we put all of our p's over our q's. 1 over 1 gives us 1, so we get plus or minus 1. 2 over 1 is 2, so we get plus or minus 2. 4 over 1 is 4, so plus or minus 4. We have 6 possible rational zeros. Any questions so far? All right, then let's just start going down the list. Let's start with the negative 1. My coefficients are 1, negative 2, negative 5, 8, and 4. Skip a little space and draw our line. We bring down the 1. Negative 1 times 1 is a negative 1. When we add here, I get a negative 3. Negative 1 times a negative 3, that's a positive 3. When I add here, I get a negative 2. Negative 1 times a negative 2 is a positive 2. When I add there, I get a 10. Negative 1 times 10 is a negative 10. When I add, I get a negative 6. Negative 6 is not 0, so negative 1 is not a 0. Moving on to the next one, a positive 1. 1, negative 2, negative 5, 8, and 4. Bring down the 1. 1 times 1 is 1. When I add negative 2 plus 1, that's a negative 1. 1 times a negative 1 is a negative 1. When I add, I get a negative 6. 1 times a negative 6 is a negative 6. When I add, I get 2. 2 times 1 is 2. When I add, I get 6. So neither 1 nor negative 1 is a 0 of our function. I'll go to negative 2. Bring the 1 down. Negative 2 times 1 is a negative 2. When I add here, I get a negative 4. Negative 2 times a negative 4 is a positive 8 when I add here. Negative 5 plus 8 is 3. Negative 2 times 3 is a negative 6. When I add, I get a positive 2. Negative 2 times a positive 2 is a negative 4. I've finally found 1, 0. Okay. So far, nothing different really is going on with this fourth degree polynomial. But remember what we've done with the cubic is once we found 1, 0, we got to go to the quadratic formula. Because the remaining coefficients were the coefficients for quadratic. But that's not the case here. We started with a fourth degree polynomial. Now that we found 1, 0, those coefficients that you see there, the 1, the negative 4, the 3, and the 2, those are for a cubic, a degree 3 polynomial. So in this case, you want to keep going with synthetic division. Only when you have 3 coefficients down here do you want to go to the quadratic. Because this is not quadratic, so the quadratic formula is not going to work. If you were to think about this, you might have an A, a B, and a C, but what's this? You know? So you can see that the quadratic formula is not going to work. So now I'm going to use these as my reduced polynomial. Maybe just being a little bit more explicit and kind of refreshing where we've been. Remember, if negative 2 is a 0, x minus a negative 2, which is x plus 2, is a factor. So right now, what do I know? This factors as an x plus 2, and then this is my cubic polynomial. X cubed minus 4x squared plus 3x plus 2 is essentially what we've done so far. And so this that remains, these are the coefficients on the cubic polynomial. Okay? So now I'm going to use these coefficients, and I'm going to keep going. Remember, you can have a repeated root, so let's go ahead and try negative 2 on these coefficients. But just, you don't need the 0, because that was the remainder. Because now I'm seeing, does negative 2, is that a 0 of this cubic polynomial? So I draw my line, I bring down my 1. Negative 2 times 1 is a negative 2. These add to give me a 6. Negative 2 times a negative 6 is a positive 12. Those add to give me 15. Negative 2 times 15 is a negative 30. Those add to give me a negative 28. So 2 is not repeated. It is a 0, or negative 2, I'm sorry. It is a 0, but it's not a repeated 0. Does everyone understand why I tested it again? Remember the negative 1 a minute ago? It was repeated. And so we want to make sure that we're not missing a repeated 0. Okay. So negative 1 and 1, they're already out. Negative 2 is in, but just once. So now we're going to try the positive 2. So I'm going to put the positive 2 in the box with my reduced degreed coefficients. I'm going to bring down the 1. 2 times 1 is 2. These add to give me a negative 2. 2 times a negative 2 is a negative 4. Those add to give me a negative 1. 2 times a negative 2 is a negative 2. I've got my 0 there. So both negative 2 and positive 2 are zeros. Started with a fourth degree polynomial. When I found a 0 of negative 2, that gives me a cubic polynomial. When I found the 0 of 2, these coefficients are now quadratic. Do you see how that works? So I can use the quadratic formula on this one. You can use the quadratic formula when you have the 3 remaining numbers in front of the 0. That's when you know you have the quadratic, your A, your B, and your C. So this is my A, this is my B, and that's my C. Negative B plus or minus the square root of B squared minus 4 times A times C all over 2A. So that's 2 plus or minus the square root of 4 plus 4, which is 8, all over 2. Remember that 8 is 4 times 2? So if I take the square root of 4, it's going to give me a 2 out front. So this gives me 2 plus or minus 2 square roots of 2 all over 2. Everything divides by 2 to give me 1 plus or minus the square root of 2. And that gives me my remaining 2 roots. I knew I was looking for 4. Root 1 was the negative 2. Root 2 was the positive 2. Roots 3 and 4 are right here. Okay? And so my actual zeros, my solution, negative 2, positive 2, 1 plus or minus the square root of 2. Those are my 4 zeros. This is a very repetitive process. Now, if your P's and your Q's have a lot of factors, it gets monotonous for sure, because you will probably try a bunch and not get zeros maybe for a while. And the higher degree your polynomial is, of course, the more repetitions you have to get because you're looking for all of those zeros. Jaron.
What's that x plus 2 numbers up there where you wrote the
Yeah. So in class on Wednesday, we had a rule that said if x minus c is a factor, then c is a 0. And then we also had the backwards way. If c is a 0, x minus c is a factor. So when you think about your polynomial, if you write it in factors, you know, that's where you're looking to factor it, such as that. So what you saw here came from this statement here. We had found a 0. A 0 was negative 2. So negative 2 was a 0, so x minus a negative 2, so that's x plus 2 is a factor.
Okay.
Good question. And so once I had factored out that x plus 2, then the other factor came from these coefficients right here. So I had a 4th degree polynomial. I have 1 degree taken care of with this factor. So that must mean that the remaining polynomial is a cubic.
Okay.
So there's a lot of little tiny details that all fit together here. Does that make better sense? Good. Great question. All right. Anybody else? Great. The fundamental theorem of algebra just says this: if f of x is a polynomial of degree n where n is greater than or equal to 1, then the equation f of x has at least one complex root. Nothing earth-shattering, I think, when we've already talked about the properties over here. We know that an nth degree polynomial has n roots. It just says what we're saying is that they're not all real. So the complex numbers include the real numbers, and so it's just saying there is a solution. It may not be real, though. And then that takes us to the linear factorization theorem, and Jaron set us up perfectly for this. It says if you have a polynomial where n is greater than or equal to 1 and a sub n is not 0, so you've not zeroed out the nth term, then the function can factor into n linear factors of x minus c's. So again, remember that when we factor it, the minus sign is in the formula. And so just like we were talking about, and so if C1, C2, and Cn, they're complex numbers, possibly real, not necessarily distinct, but in words, an nth degree polynomial can be expressed as the product of a non-zero constant, that's your a sub n, and n linear factors. Remember, a linear factor just has an x to the first power. And so these are all linear factors. So this can help us factor higher ordered polynomials, which is super important. How would we factor cubic polynomials and such? Okay. So this one is a good example. It shows all the pieces kind of put together from what we did in section 3.3 and now in 3.4. It says find a third degree polynomial function f of x with real coefficients that has 1 and 5i as zeros, such that f of -1 equals -104. So that's a whole lot of words on there. What do we know? It's going to be a third degree polynomial. That tells us that our n is 3. Also, remember, just what we were saying a minute ago, if c is a 0, x minus c is a factor. How many zeros will my polynomial function have? 3, exactly. I'm looking for 3 zeros. So let's just list our zeros real quick. They tell us that 1 is a 0 and 5i is a 0. Well, how can we find the third one? They didn't give it to us. Anybody know?
Division?
Not division. If a plus bi is a root, a minus bi is a root. So the imaginary piece, if you have an imaginary 0, you just change the sign on the imaginary 0, and that gives you your other 0. Conjugate pairs. And so here, since 5i is a 0, negative 5i is 2. The conjugate pairs theorem. Okay. So those are our zeros. Let's think about the factors now, the linear factors. If you know a 0, x minus that value is a factor. So if 1 is a 0, x minus 1 is a factor. Yes, Jaron?
Why wouldn't -1 be a 0 too?
Because they don't occur in pairs. And so the conjugate pairs theorem says a plus bi is a factor or a 0, then a minus bi is. A is the real piece. Notice it keeps its sign here. So since 1 is real, we don't get a distinct pair with just the 1, because b for the number 1, the b is 0. And so we only change the sign on the imaginary part. If 5i is a 0, x minus 5i is a linear factor. If negative 5i is a 0, x minus negative 5i is a factor, which is x plus 5i. So, putting together this with our linear factorization theorem, we have our 3 linear factors. We knew we'd get 3 because we have a degree 3 polynomial. The only thing we're missing is this a sub n out front. Okay? So, I know my function f of x will equal some number times x minus 1 times x minus 5i times x plus 5i. If I know a 0, then I know the factor. If I have an imaginary 0, its conjugate is also a 0. Okay? Any questions on how we got where we are so far? Let's go ahead and multiply this part out to help us with the remaining piece. So that f of x will equal a sub n. I'm going to keep the x minus 1 out first, and I'm going to use full to help me multiply x minus 5i times x plus 5i. First, x times x is x squared. Outer is x times 5i, which gives me positive 5ix. Inner, negative 5i times x. Last, I have a negative times a positive, which is a negative. 5 times 5 is 25. I times I is I squared. Those two middle terms do add to give me 0. So I have a sub n times x minus 1 times x squared, negative 25 times I squared. What is I squared? Negative 1. So negative 25I squared is negative 25 times a negative 1, which is a positive 25. So this just gives me plus 25 in here. Keeping my a sub n out front, I can use FOIL one more time. First times first gives me x cubed. Outer gives me 25x. Inner gives me negative x squared, and last gives me negative 25. So I'm starting to see that cubic polynomial coming through. And if you like, you can write that in descending powers on x. Okay. So we were given one last little bit of information. We were told that when I plug negative 1 into my function, I need to get out a negative 104. That's how you figure out what a sub n is. So that f of negative 1 will be a sub n times negative 1 cubed minus negative 1 squared plus 25 times negative 1 minus 25. I'm just plugging the negative 1 in. Negative 1 cubed is a negative 1. Negative 1 squared is a positive 1, but it follows another negative, so I've got a minus 1, minus 25, minus 25. That gives me a sub n times a negative 52. And I know that that's supposed to equal negative 104. So that equals negative 104. So a sub n will be negative 104 divided by negative 52, which is a positive 2. Because I have a sub n multiplied by negative 52, and I'm trying to figure out what a sub n is. So to undo this multiplication by negative 52, we'll divide. Yep. Okay. So that, you can finish your polynomial. Going back right here, here's what our polynomial is. It says my a sub n is 2. So this becomes 2 times x cubed minus x squared plus 25x minus 25. That's your polynomial. You can distribute the 2 through to give you 2x cubed minus 2x squared plus 50x minus 50. Okay. Mathematically, there's nothing too difficult in this, but there are so many details. All of the pieces start to fit together. All of these theorems, the linear factorization theorem, the complex conjugate zeros piece. If C is a factor, X minus C is, if C is a 0, X minus C is a factor. So many things are all tied up into this problem. You will more than likely have one very similar to this on your quiz on Wednesday, because this ties all the pieces together. Any questions on this example? We want to go walk through it again, or you feel good? Again. First of all, it says we had a third degree polynomial function. N is 3. I know I'm going to have 3 zeros, and each zero will go to a factor. I was given a 0 of 1, so x minus 1 is the linear factor. I was given a 0 of 5i, so x minus 5i is a linear factor. But since 5i is a 0, negative 5i is also a 0. So x minus a negative 5i, which is x plus 5i, is a linear factor. I have my linear factors. I've multiplied them times each other with an a sub n out front, the leading coefficient. Just go through all that multiplication until you have it all multiplied out. You take your last bit of information. This says when I plug negative 1 into my function, the result needs to be a negative 1/4. And that's where we get our a sub n. Okay. Again, mathematically, nothing too terribly hard, but a lot of little details that go in to getting this right. I want y'all to get this one started. We'll go through the multiplication, but I want you to set this up. I want you to list the zeros, list the factors, and then get the form of the function. F of x is equal to a sub n times those linear factors. So get started on this one. Let me know if you need some help. So as far as you getting started, I just want you to go to the similar step as to this right here, where you've got the a sub n and the linear factors. We'll go through the multiplication together. Okay? Unless you're already done and you want to get started on that, then you can. So they tell us we're looking for a third degree polynomial. That means I'm going to have 3 zeros and 3 factors. So my zeros of this function, they tell me that 6 is a 0 and negative 5 plus 2i is a 0. That's 2 out of the 3 zeros. What's the remaining 0? It's negative 5 minus 2i. I'm glad you said that, because remember that the conjugate pairs come in this form. So it's only the b part that changes sign. You keep a, change the sign on b. Okay? So if negative 5 plus 2i is a 0, we keep the negative 5, but we change the sign on the 2i. So negative 5 minus 2i is also a 0. If 6 is a 0, x minus 6 is a factor. Okay. If negative 5 plus 2i is a 0, x minus negative 5 plus 2i is a factor, which tells me that this is x plus 5 minus 2i when you distribute that negative sign through. If negative 5 minus 2i is a 0, x minus negative 5 minus 2i is a factor. So again, that minus sign distributes, and this becomes x plus 5 plus 2i as the factor. Okay. So that our function f of x will be a sub n times x minus 6 times x plus 5 minus 2i times x plus 5 plus 2i. Any questions on getting the form to this point? All right. Well, this is not full anymore, but it's just distributing. I'm going to keep the a sub n and the x minus 6 out front. I'm going to take the x from our last factor and distribute it through all of the terms here. X multiplies by x to give me x squared. X multiplies by 5 to give me 5x. X multiplies by negative 2i to give me a negative 2ix. Okay, that was just taking this x and multiplying it through to each. I do the same thing with the 5. 5 is going to multiply by x to give me 5x. 5 multiplies by 5 to give me 25. 5 multiplies by negative 2i to give me a negative 10i. And I'm done with the 5. Now I take the 2i. 2i multiplies by x to give me a positive 2ix. 2i multiplies by 5 to give me a positive 10i. 2i multiplies by a negative 2i to give me a negative 4i squared. After you've multiplied the two conjugate factors together, you should be done with all your i's. The i's should eliminate, and let's see if they do. I have a negative 10i and a positive 10i. Those do add to give me 0. I have a negative 2ix and a positive 2ix. Those add to give me 0. Remember that the I squared is a negative 1, so that we get negative 4 times a negative 1, so this last thing is a positive 4. Now then we can combine like terms. I have x squared. I have 5x's plus 5x's, that's 10x's. And I have 25 plus 4, so I get 29. I'll distribute another time. I'm going to take each one of these three terms, distributing it through the x and the negative 6. X squared times x is x cubed. X squared times a negative 6 is a negative 6x. 10x times x is 10x squared. 10x times a negative 6 is a negative 60x. 29 times x gives me 29x. 29 times 6, I think, gives me 174 negative. Combining like terms, We have x cubed. I forgot a square somewhere. Where? Right there. And right there. Man, I forgot two of them. Sorry about that. This should be x cubed minus 6x squared plus 10x squared. Minus 60x. So that I get plus 4x squared minus 31x minus 174. Finally, I know when I plug 2 into the function, I need to get out a negative 636. So that f of 2 will be a sub n times 2 cubed plus 4 times 2 squared minus 31 times 2 minus 174. What do we get there? We get 8. And then 2 squared is 4 times 4, so plus 16, minus 62, minus 174. I get negative 212. Multiplied by an. All of this is negative 212. It's multiplied by an. I know that the output needs to be negative 636. So that a sub n is negative 636 divided by negative 212, which is 3. So then when you finish writing this, you just plug in the 3 there and distribute it through to your polynomial. Oops. For the sake of time, I'm not going to do that last step. It looks just like what we finished with on the prior example. These work the same every single time. We happen to just do third-degree polynomials, but there's no reason why you couldn't do higher-order polynomials than 3. All right. This right here. So we found a sub n. I'm saying just plug in 3. Right there, yeah. The angle was kind of bad. So you'd get 3x cubed plus 12x squared minus 93x and then minus 174 times 3, whatever that is. Okay? All right. Then we still have one last piece here, Descartes' rule of signs. Descartes' rule of signs is just another technique that can help us when we've got our list of possible rational zeros. It can help us figure out ways to potentially eliminate some of those possible rational zeros once we get down the list. So we're starting off with our polynomial, and Descartes' rule of signs says this: the number of positive real zeros of f is either the same as the number of sign changes of f of x or less than that by an even integer. An even integer will be multiples of 2. If f of x has only one variation in sign, then f has exactly one positive real zero. This all sounds like a whole bunch of jumbled up words on the page. We'll make it easy for you in a minute. Then, if we want to find the number of negative real zeros, it's the same idea, but it's the same as the number of sign changes of f of negative x, or less than that by a positive even integer. So our last example here says determine the possible number of positive and negative real zeros. So when we're talking about positive, you take your function, you make sure that it is written in descending powers of x, and ours is. We started off with a fourth, then a third, then a square, then an x, and then our constant. Okay? Now we're just looking for sign changes in the coefficients. X to the fourth, it has a positive implied out front, positive 1. Positive to negative. Did we change sign there? Yes, we did. I'm going to put a number 1 down there. I'm counting sign changes. Positive to negative, that's a sign change. Negative to positive, that's another sign change. Positive to negative, that's another sign change. Negative to positive, that's another sign change. If I add these up, 1 plus 1 plus 1 plus 1 gives me 4. So Descartes' rule of sign says this. The number of positive real zeros of f is either the same as the number of sign changes, that's what we just found, or less than that by multiples of 2. So, if I subtract 2 from 4, I get 2. If I subtract 2 from 2, I get 0. So once you've got your number of sign changes, just keep reducing that number until you get down to 1 or 0. If the number of sign changes is odd, you'll get down to 1. The number of sign changes is even, you'll get down to 0. So it means that this polynomial will either have 4, 2, or 0 positive real roots. It will not have an odd number of real roots. Now, to get the negatives, we do the exact same thing, but with f of negative x. So that will be negative x to the 4th minus 14 times negative x cubed plus 71 times negative x squared minus 154 times negative x plus 120. So you're just plugging in negative x into your function. Negative x to the 4th, well, a negative to an even power is positive, so that's just an x to the 4th. Negative x cubed, a negative to an odd power is negative, so it will multiply by the 14 to give me positive 14x cubed. Negative x times a negative x is a positive, so we get 71x squared. We'll get plus 154x plus 120. Let's look for our sign changes. X to the 4th is positive. We have a positive to a positive. The sign didn't change, so I'm counting sign changes. That's going to give me a 0 down there. If it changes, I write a 1. If it doesn't change, I write a 0. Positive stayed positive, it's 0. Positive stayed positive, it's 0. Positive stayed positive, it's 0. I have 0 negative real roots. That's really pretty quick and simple. Now think about this. If we had a long list of possible rational zeros, what would this tell me? Don't put any of the negative ones in the box. They're not going to be your answer. So that eliminates half of those possible rational zeros. So this is just a time saver. Especially if you have a lot of possible rational zeros. When you get something that looks like this, it's telling me I have no negative roots in here. So let's don't try them. All of my roots are going to be positive. The real roots. I may have complex or imaginary roots, but my real roots. All of my real roots will be positive. All right, with 30 seconds to spare.